Here is the next topic. In this topic, we're going to find transfer function from the state equation and output equation. In the previous videos, we learned that how to find state equation and output equation from electrical circuit or from mechanical system or from a mathematical equation, which is nothing but a transfer function. Okay, so here is the output equation: x dot equal to ax plus bu. This is my output equation. Y equal to cx plus d. Sorry, this is my state equation. That's my state equation. Y equal to cx plus du. That's my output equation. Now h of s is nothing but the transfer function, which is output over input. S is nothing but which is in S domain, Laplace domain, where all the initial conditions are 0. Now that x dot ax plus bu, that x dot is in time domain. I'm converting that into S domain. We know that x dot is nothing but dx over dt, which is nothing but s times x of s when I convert that into S domain. So when I convert this into S domain, the state equation into S domain, which is s times x of s equal to ax of s plus bu of s. Everything is in S domain. So now I'm going to pull ax of s to the other side. So it's going to be s x of s minus x of s equal to b times u of s. So if I pull out the x of s, it's s minus a x of s. Now s is a scalar. You have only one s, and a is in the matrix format. You cannot subtract a scalar quantity from the matrix. So what I'm going to do, I'm going to multiply this s with the identity matrix I. Okay, where I is the identity matrix. So we know that when you multiply something with identity matrix, you will end up with getting the same thing. So if I multiply s with identity matrix, I will end up with the s. So now this si minus a, I'm going to move it to the other side. When I move to the other side, it's going to be inverse si minus a, inverse times b u of s. Now I'm going to take the output equation y cx plus du. So y of s equal to cx of s plus du of s. Now I'm going to substitute x of s in there. Once I substitute it, y of s equal to c times si minus a inverse times b u of s plus d u of s. Now I'm going to pull u of s as it's a common in both parts of the equation. What I'm going to do, when I pull it to the other side, it's going to be y of s over u of s, which is nothing but transfer function h of s. So h of s equal to c times si minus a inverse times b plus d. That's how, by using this equation, we can find out the transfer function from the state and output equation. So here is the first example. X dot equal to minus 3, 1, minus 2, 0. X1, x2 plus 0, 1, u. So y equal to 1, 0 and d is 0. So basically from here I can tell that's my A matrix, that's my B matrix, C matrix, and D matrix is 0. Nothing is given. So h of s equal to c times si minus a inverse times b plus d. This is the equation or formula to find transfer function. Now I'm going to find si minus a. So s 0, 0, s minus 3, 1, minus 2, 0. So si minus a is nothing but I will end up with s plus 3, 0 minus 1 minus 1, 0 minus 2, minus of minus 2 plus 2, and s. Okay, now I'm going to find si minus a inverse. Okay, it's a 2 by 2 matrix. If you remember, some p equal to, let me write this separate. Say if you have p equal to a b c d matrix, now p inverse equal to 1 over ad minus bc, d minus b minus c, a. That's how you'll find p inverse. Same way we'll find si minus a inverse equal to 1 over AD minus BC. So S plus 3 times S minus of BC is 2 times minus 1, 2 times minus 1. Okay, now here S plus 1 minus 2, S plus 3. Okay, so Si minus A, if I simplify this is going to be, I'm pretty much sure, S square plus 3S plus 2. It's a perfect equation. I can get two poles out of it, which are is it 1 over S plus 1 and S plus 2. Okay, S square plus 3S plus 2. Okay, perfect. Now this S1 minus 2, S plus 3. This is Si minus A inverse. Now I'm going to write down C times Si minus A inverse. Here I have C equal to 1 0. Okay, so 1 0 times S1 minus 2, S plus 3. I'm going to keep this constant right here. It doesn't matter where do you write it, after or before. So this is 1 by 2, that's a 2 by 2. So when we combine these two, make sure that these two numbers are same, then only we can multiply. And the resultant matrix size is going to be 1 by 2. So here we'll end up with 1 times S and 1 times 1 over S plus 1 times S plus 2. Okay. Now I need to multiply this with B. So C times Si minus A inverse times B, which is 1 over S plus 1, S plus 2 times here S and 1. This is 1 by 2 matrix. B, I have 0 and 1. Is that right? What do you have B? So the given matrix B, I have 0 and 1. Okay. Now what is the size of this matrix? This must be 2 by 1. Okay. As long as these two numbers are same, we can do the multiplication. Now the result is going to be 1 over S plus 1 and S plus 2, or you can say 1 over S square plus 3S plus 2. This is Y over U in S domain. If you want, you can convert this into time domain, or as long as I see this answer, I'll give you full credit. So this is the transfer function. Here, this denominator, we know that we call this as characteristic polynomial. When we make it equal to 0, we call it as characteristic polynomial equation. Let me solve one more example in this. Here is the next example. You can clearly see, I mean, with the A matrix, you have the elements on the, the elements are in the, those are the diagonal elements. So if you see diagonal elements and the other elements are all 0, that's a Jordan form basically. So A equal to 3002, B equal to 21, C equal to 1 minus 1. So now to find H of S equal to, I'm going to use different color, C times Si minus A whole inverse times B plus D. Here I don't have any D, so okay. For time being, let me add one more element, say plus 2U. So assuming there is a D element too. I'm extending this example a little bit. So first thing, we're going to find Si minus A. Okay, S is S00S minus A is 3002, which is S minus 300 S minus 2. Si minus A whole inverse equal to 1 over AD minus BC. So AD is S minus 3, S minus 2, BC is 0, and S minus 2, 0, 0, S minus 3. Now it doesn't matter which one you do first, C times Si minus A whole inverse. so which is equal to s minus 3, s minus 2. I'm going to keep it on the side. C is 1 minus 1, s minus 2, 0, 0, s minus 3. Now when we multiply this, 1 over s minus 3, s minus 2, when we multiply this, we'll end up with s minus 2 and 0. Not 0, actually it's minus s minus 3. Now I'm going to multiply this with b, si minus a whole inverse times b, which is 1 over s minus 3, s minus 2, s minus 2 minus of s minus 3, and B matrix we have 2 and 1. Is that right? Yeah, B equal to, that's a 2 and 1. So we'll end up with 2 times s minus 2 minus s minus 3 over s minus 3 times s minus 2. So further simplify, I will end up with 2s minus 4 minus s plus 3 over s minus 3, s minus 2. Now I have d component 2. So this, if I simplify this, this is going to be basically s minus 1. Now I have d component. So h of s equal to c times si minus a whole inverse times b plus d, that equal to s minus 1 over s minus 3 times s minus 2 plus, I think d component I gave you as a 2. Okay, 2 is the d value, plus 2. So you can do the LCM, you will end up with s minus 3, s minus 2 divided by s minus 1 plus 2 times s minus 3 and s minus 2. Okay, so after further simplification, it has poles at s minus 3 and s minus 2. There are 2 poles. Now the numerator, after simplification, I have 2s square minus 9s plus 11 over s minus 3 and s minus 2. So you can see it has equal number of poles and zeros. So when are you going to have equal number of poles and zeros? When there's a d component in the state in the output equation. Okay, thank you. I'll stop it here. Next example, probably I'm going to solve a 3-state variable matrix.